Okay, so in this video I want to talk a little bit more about water and acids and bases. So as you probably know, water is H2O, and we can represent that as this, which, as I said before, there's electron density drawn from the hydrogens into the oxygen, and if you add these two things up as vectors, it gives you an overall polarity to this molecule. Whereas when I talked about hydrocarbons, which we can represent this way, I said that there was that van der Waals force, van der Waal. So there is some what's called intermolecular force, intermolecular force. That's what this van der Waals forces are, but these are somewhat weak. As the hydrocarbon chains get longer, the van der Waals force becomes stronger because you just have more places on the chain where these sorts of forces are taking place. So as these van der Waals forces get stronger, the melting temperature of the substance starts increasing. So something that has a really long hydrocarbon chain is more likely, or it's going to be solid at a higher temperature, whereas something with only a few carbons, say butane, which is shown here, is going to be liquid, like what you see in your lighter. Then if you get even smaller chains, like ethane or methane, these, and even propane, these are going to be gases at room temperature. Okay, so we see this trend in hydrocarbons where van der Waals forces are the main forces. So water is this relatively small molecule compared to these hydrocarbon chains, and yet this is liquid at room temperature. So how does that happen? Magnets, how do those work? So in water, we have, instead of van der Waals forces or van der Waals intermolecular forces, we have what are called hydrogen bonds. So the partial negative here and the partial positive here form these sort of pseudo bonds with each other, which causes these molecules to stay more closely packed together, so that even at room temperature this is still liquid, which is, one of the remarkable features of water. And another remarkable feature of water is that when it is frozen in a solid state, it aligns into these sort of crystal structures that we see as ice, which maintain these regular distances between the molecules. And that's why, so if we have liquid water, so we could have another water right here and another water sort of crammed in here. They're all crammed together, but then when we lower the temperature to freezing, these actually align at these regular distances. And that's why frozen water or ice is less dense than liquid water. That's why ice floats in liquid water rather than sinks. You would usually think that something that's solid is more dense and that would sink in its liquid form, but that is in fact not the case with water. So another interesting thing about water that we need to take into consideration is that it undergoes what's called autoionization. So we have these two water molecules, there's this hydrogen bond between them. Well, sometimes this hydrogen bond becomes a real bond, and then this real bond goes away. So what we end up with is HO with a negative charge, and then O with 3 H's with a positive charge. This is called a hydroxide, and this is called a hydronium. And this, it happens, but not very often. So this is, like I said, it's called autoionization, and that can be represented in a chemical equation like this: OH minus plus H3O plus. So this happens at a rate that's, so, alright, in the next video I'm going to get more into the idea of equilibrium and things like that, but for now I will just introduce this idea that we have this constant that I'm just going to call Kw that represents an equilibrium constant, and that is the product of the H3O plus concentration with the OH minus concentration. In chemistry, when we talk about concentrations, we often put it inside these square brackets like this. You'll see that even more in the next video. So the product of these concentrations at any given time when you're looking at some water is going to be equal to 1.0 times 10 to the negative 14. So that's a pretty small concentration of both of these. So you can get the concentration of one of them. So we know that because this H2O splits into one of those and one of those, that the OH minus is going to be equal to the H3O plus. And so we can say that the square root of Kw is equal to H3O plus squared, the square root of that, and the square root of 1 times 10 to the negative 14 is 1 times 10 to the negative 7, which is, so if we, not equal, if we take that and then do the negative log of 10 to the negative 7, we get 7. And this is how we define pH. So that's why when water is neutral, it has a pH of 7. So that's where that number comes from, is just taking this concentration, and since these are both equal to each other, it's basically the same thing squared. So then you take the square root of both sides and you get this 10 to the negative 7. The negative logarithm of that is 7. That's how you get your pH equals 7. So to sort of justify what this is here a little bit, or maybe this to be more accurate, is it's not that there is just always this OH that's floating around in your water. This is surrounded by water, and your H3O plus that it's sitting around in the water. It's that water is constantly undergoing this autoionization where this hydrogen bond becomes a real bond, and then this pair of electrons gets shoved over onto that oxygen, so that you end up getting these two species. So this reaction happening in this direction is always happening, but as you can see here, I suggestively used what's called the equilibrium arrows, because the other reaction is always happening as well, such that we always, at any given time, if you had a glass of water and you were able to take a picture of every molecule in it, you would always find that there are this many H3O plus and OH minus, or that the product of the two is always going to equal this 1.0 times 10 to the negative 14, such that the product, or the concentration of just one of them, is this 10 to the negative 7. And the units I should put on that is molarity, which is the mole per unit volume, which is in liters. And a mole is just a really large number of molecules. So 6.02 times 10 to the 23rd molecules in a single mole. So there are 6.02 times 10 to the 23rd moles in 1 liter gives you 1 molarity. So this right here is, in molarity, is usually shown in a large M. So this is large M. So it's kind of a small molarity where, you know, there isn't very much of these, of either of these species in the water, but this forward and backward reaction is always taking place in what's called dynamic equilibrium, which I will go into more detail in the next video. In this video, though, I want to talk about acids and bases. So this right here is your sort of quintessential acid, and this is your quintessential base. And the reason for that is, if we have a hydronium like this, which has this extra hydrogen on it, and the hydroxide like this, which is missing a hydrogen, this is going to want to snatch that off of there and become 2 H2Os once again. So this is sort of the quintessential acid-base reaction. This here being a base, this here being an acid, with acids being molecules that want to donate or get rid of a hydrogen, and bases being molecules that want to take on hydrogens. And so, like I was talking about in the previous video, we can have an acid that's like the carboxylic acid that has this H on it, and we can take another, maybe hydroxide, and this will come and try and take that hydrogen off of there, turning that into the carboxylate and H2O. So this is another acid base, and you can also do it as hydrochloric acid, one of the more famous types of acid, and maybe a hydroxide, and that will take that and that will go there so that you end up with chloride ions plus H2O. So this sort of acid-base framework where we're always talking about hydrogen ions, the H plus ions, is known as Bronsted-Lowry acids and bases. And this tendency to give up a hydrogen is something that chemists like to put a number to. It's a number that says how likely this is to give up its hydrogen, how likely this is to give up its hydrogen. And that number is what's known as the pKa. And the lower this number is, the more acidic something is, the more likely it is to give up that hydrogen. And a carboxylic acid like this, which I always take as sort of the quintessential weak acid, has a pKa of about 4.7. So if we're in the pKa range of about 5, we're probably in the very weak acid range. Whereas hydrochloric acid, which everybody knows is a very strong acid, has a pKa of negative 6.3. So you can see that's quite a bit lower than this, signifying that this is in fact a quite strong acid. And then I talked about in the last video too about sulfuric acid, H2SO4, which has a pKa of negative 3. So hydrochloric acid, very strong, has this very low pKa. This has a pretty low pKa, so it's a strong acid. And of course, with H2SO4, you actually end up having two different pKa's because it can lose one of its hydrogens and then it becomes HSO4 minus. I don't know the pKa of this other hydrogen off the top of my head, but that pKa, which we'll call this pKa1 and this pKa2, will be greater than pKa1. The reason for that is, if you look at the SO4, so if this is with one of its hydrogens already taken off, this is being resonance stabilized by these two oxygen double bonds. So this charge is sort of spread over the rest of this molecule. But if we wanted to get rid of this one, then we'd have two charges that we have to spread over this molecule. So it's not going to give up this hydrogen nearly as quickly as it's going to give up this first hydrogen. So an acid species like this will actually have more than one pKa. But when we're talking about, something that's this simple carboxylic acid, then it's going to have this single pKa, which is about 4.7. This hydrochloric acid is going to have a single pKa, which is negative 6.3. That's very strong. But this Bronsted-Lowry conception of acids is, it's a very narrow conception of acids. There is also what is called the Lewis acid. So in Lewis acid theory, instead of just H+, it can actually be any sort of atom or ion that wants to bind to something that has two free electrons. And we call these things nucleophiles. Nucleo because this is just a nucleus, and phile, which means love, so it loves nuclei. So this nucleophile wants to bind to something that has positive charge, or something that has sort of an exposed nucleus. So in Lewis acids, instead of just hydrogen ions, we can actually count other things that are in these Lewis acids can also be called electrophiles, because just like the nucleophiles love nuclei, electrophiles love electrons. So they're kind of a match made in heaven. So if we have something like iron 3 plus, then we can have some kind of nucleophile, which maybe we'll say is our OH minus. So this is our nucleophile, sometimes just shortened to nuke, and this is our electrophile or Lewis acid. So this is going to want to bind to that, which would make this, since this has a negative charge and this has 3 positive charges, bonding to one of these is going to lower its charge by 1. So this is the way that something even besides a hydrogen ion can act as an acid. And sort of a cheat way that I like to think about it, because the Bronsted-Lowry is, it's a very simple way to conceive of acids. An acid is just something that wants to give up a hydrogen ion, or a hydrogen ion in general is the acid. So if we want to think about Lewis acids and we want to put that in terms of our Bronsted-Lowry acid, then we can think of it this way. So it's in water. It's not going to be as strong of a nucleophile as this, because this has that charge on it. But water can still act as a nucleophile. That's sort of what it was doing up here when we were having it take off the hydrogen from this other water. This was the water acting like a nucleophile. It's going after this hydrogen atom, which is basically just a proton. It's a nucleus. And so this can be seen as a nucleophile, which is going to go after that iron. And then we end up with iron 2 plus bound to this water, and this will have a plus on it. And so in order to get rid of this charge on the electron, on the oxygen, these electrons are going to go over there, and so we end up with Fe2 plus going to this plus our hydrogen ion. So we can still sort of conceive these Lewis acids in a nice, easy Bronsted-Lowry conception of acids and bases. So we can still think about it as just a hydrogen ion. One other thing that I want to cover in this video is, I was talking about solubility above. So up above we use the Kw for our acid base, but in solubility we usually use Ksp. You'll see, especially in the next video, that these equilibrium constants are always K, and then they just have different subscripts. So this could be something like sodium chloride, which is your regular table salt, and this is how much it's going to be soluble in water. And for table salt, I believe this equals about 37 at 25 degrees Celsius. And once again, in the next video, we'll see that temperature has a lot to do with the equilibrium, and this is a sort of equilibrium. So this means that you're going to end up with the square root of 37 as your concentration of sodium and chloride in moles per liter in your solution. And when you have something like sodium and chloride dissolved in solution, the way that occurs is that sodium, which has that positive charge, is going to be surrounded by water molecules that are making partial bonds similar to the hydrogen bonds. This is a hydrogen, or this is a bond to a fully charged particle rather than a partially charged particle. So these waters are going to align all around the sodium ion, and that's what's keeping it separated from the chloride ion, which is surrounded in the opposite way, where the positive and partial positive on the hydrogen is attracted to the negative charge on the chloride. So these water molecules are actually keeping these ions separate from each other, and oops, that should be oxygen, and that's how something like sodium and chloride dissolves in water. So when when any ions are dissolved in water, you have something like a glass of water here that has a certain concentration of sodium and a certain concentration of chloride. And if you took this and then dumped it into a larger container that was at half water, so that you put this water into it. This water has no sodium and chloride in it, and this water has no sodium and chloride in it. This water does have it in it. So when you put it in, you double the amount of liquid in there. That will cut the concentrations of these things in half, because now you have double the volume. So let's say this was 1 liter, and we had exactly 1 mole of sodium and 1 mole of chloride. So now after dumping it in there, we're going to have a mole per 2 liters. And so our concentration reduces. So that's called a dilution. And when you put this water with the sodium chloride into the water with nothing in it, that sodium chloride is going to immediately start dispersing throughout all of the water in what is called diffusion, so that after a certain amount of time, all of the water in this container, if you took out some sample from here, or if you took out a sample from here or from here, they're all going to have the same concentration. So that is what diffusion is. And one last concept. So if we have a container of water and say we have a permeable membrane in it, and then we add, say we have water in here, and we add sodium chloride to this side so that this part of the container is getting the concentration of sodium chloride, and this has none. What's going to happen is the sodium chloride is going to move through this permeable membrane. It allows the ions to move through it. Then at some point we're going to get to a place where this has a high concentration of sodium chloride and this has low, and you're still going to have sodium chloride moving across this membrane into this side, but you're also going to have a little bit moving, put the water there, from this side to this side. But the rate at which it's going from the high side to the low side is much faster than the rate at which it's going from the low side to the high side. So if you leave it for even a little while longer, you are going to end up with the concentration here being equal to the concentration here. And this process is called osmosis, where the ions are moving across this permeable membrane from a place where it's a high concentration to a low concentration. But of course, you can actually do things in an opposite way, which is if this membrane does not allow the sodium or the chloride to move across this membrane, then you're actually going to have water start moving across the membrane into the other side. So it's probably not going to overcome gravity. You're not going to end up seeing this water level rise. But I'll just put it in the context of a cell. So if we have a cell which is, its membrane is semi-permeable, if you put it into some solution that has too much sodium chloride dissolved into it, then the water inside the cell is actually going to move out of the cell into the higher concentration. And the way we can sort of conceptualize that is if we have our semi-permeable membrane here. I'm zoomed in a little bit more. You would think if it's just water on both sides, then water is going to move from this side to this side just as often as water is going to move from this side to this side. However, if we now put sodium chloride on this side, sometimes there's going to be a sodium, or sometimes there will be a chloride in the way of this, preventing water from moving over here, while this water keeps moving over there. And so water is going to move towards the side that has the higher concentration of sodium and chloride. And so you're going to have water move out of your cell, which eventually will cause your cell to get all shrunk up and probably die. And the opposite can happen too, where if your cell is in a solution that is lower concentration of sodium and chloride, then water from outside is going to move into your cell, which is going to cause your cell to get really big and burst, with all the contents sort of spilling out into whatever medium it's in. And this is the reason why when you go to the hospital and you're put on an IV, they give you saline solution, because they want to give you solution that has the same concentration of salt as what is going to be inside of your veins so that you're not bursting or shrinking your cells and killing them off because of this osmosis process, what's called osmotic pressure. It's, you can think of it like the pressure of water being pushed out of the cell. It's sort of a pressure. It's osmotic pressure, or in this case, the osmotic pressure of the water going into your cell. So, like I said, that's why they give you the saline solution if you get an IV at the hospital. And so this diffusion and osmosis are related topics, but they are different. So, and they're important for a lot of nutrition and physiology and everything. So it's good to make sure that you understand these concepts. And in the next video, I am going to talk more about equilibrium and thermodynamics. And that video will probably be the most math heavy of all the videos in this entire series. But I am going to try and walk you through all of the various equations that I throw at you. So hopefully that will give you a better understanding. So I will see you in that next video.